All right, welcome everyone to the Global Water Futures Core Modeling and Forecasting Team Topical Webinar Series. My name is Praveen Rakhaya. I'm the Science Coordinator of the Core Modeling and Forecasting Team. It is my pleasure to present you today a webinar on understanding, modeling, and predicting spatial droughts and floods. Today we have Dr. Manuela Brunner from the University of Freiburg in Germany. Dr. Brunner is a lecturer in the Environmental Hydrological Systems Group, and her research focuses on hydrological extremes and changes in water resources. She develops methods to simulate and predict floods and droughts and to assess past and future changes in water cycle. Dr. Brunner obtained her PhD from the University of Zurich and Grenoble Alps, and has since worked as a postdoc at the Swiss Federal Institute for Forest, Snow and Landscape Research and the National Center for Atmospheric Research in US. Her current research covers regional droughts and floods, water scarcity, stochastic extreme flow simulation, prediction in ungauged basin, the impacts of global change on hydrological extremes and water cycle, some of which I believe she'll be highlighting today. Without taking much time, I want to kick off this webinar by thanking Dr. Brunner for accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Brunner, the floor is yours.
Thank you very much for this kind introduction, Praveen, and welcome everyone. It's a pleasure to talk in front of the GWF community about spatial droughts and floods, understanding, modeling, and prediction. I want to first take you back to the year 2005, where a widespread flood event affected wide parts of Switzerland and other countries in the area. Why do I take a picture of Switzerland? It's actually where I'm from and where my interest in floods and droughts was also shaped. On the picture, you see that the flood event caused severe damages, with gardens being flooded, cellars being flooded, and even the train station, which you can see here where my cursor is, being flooded. On the other side of the extreme spectrum, we have drought events such as the drought event 2018, which was a super important event in Europe, not just in Switzerland, where this picture comes from, but actually in other parts of Central Europe too. After such drought and flood events, which are pretty costly and damaging, we usually ask how frequent these events occur and how big they can potentially be. However, we often neglect that these events, they also have a spatial component, and that we should actually also consider spatial extent in our considerations when we ask questions about event magnitude and event frequency. Event extent is actually very relevant because it determines the potential management challenges associated with extreme events. Imagine, for example, that you have not just one location being affected by a flood, but instead 2, 3, 4, 5. You will have to dispatch personnel, emergency equipment, and also financial resources to different locations instead of being able to focus on one location. And this is just much more challenging. The same thing applies for droughts, which in normal situations can be managed by eventually transferring some water from a water-rich region to a water-poor region. But such transfers from neighboring or upstream regions, which are still water abundant, are no longer possible if several locations or all the neighboring locations are concurrently flooded. My talk today therefore focuses on these spatial flood and drought events, on their extents and spatial connections. I've structured my talk into 3 different topics, and I want to start by talking about our understanding of spatial connections between extreme events happening at different locations, and we want to look at the spatial extents of drought events. In a second part of my talk, I then want to look at modeling, and I want to present a stochastic model that simulates spatially consistent flood event sets. And in a third part, we then want to make predictions, and we want to ask questions about how frequent and how big spatially extensive events can be. In the understanding package, I'm going to talk about spatial flood dependencies and what they look like over the United States, and we're going to ask what kind of hydrometrological processes shape these spatial connections. In a second part, I'm then going to talk about spatial drought extents over the United States and how they've changed over time and because of which types of processes. In the modeling part, I'm going to introduce a stochastic model, which allows us to simulate large event sets of spatially consistent events. And we're then going to use these spatially simulated events to determine the probability of widespread flooding over 18 large river basins in the United States. As you might have noticed already, my regional focus today is on the United States, and I'm throughout my talk going to use this data set of 671 nearly natural catchments in the United States, which is also referred to as the CAMELS data set and has been developed by Nance Ador while he was working at NCAR together with Martin Clark, who you probably all know really well. So throughout my talk, I'm going to focus on these nearly natural river basins, and this being said, I'm not including or looking at how water management influences the spatial extent of events. I'm solely interested here in the natural or hydrometrological driver of spatial extremes. We first want to look at what these spatial flood connections look like and where in the United States spatial flood occurrences actually happen. In order to do this, we first start with a local analysis where we, for each of these 671 catchments, take the daily stream flow time series, define a flood threshold here illustrated by this red line, and then we extract all those events lying above this threshold, these brown dots on the figure, and we define them as flood events. And we do this for each of the 671 catchments in our data set. Once we've done this local analysis, we want to know more about what's happening in space, and in order to do this, we compile a data set that consists of all the events that have happened in any of these catchments we're looking at. In a third step, finally, we're using these events E1 to En to compile a binary occurrence matrix, which tells us for each event E and each catchment C, whether a certain catchment was affected by a certain event. If a catchment was affected by an event, we put a 1 into the matrix. If it was unaffected, we get a 0, and we can now use this binary occurrence matrix to identify pairs of catchments in the United States that have in the past co-experienced a certain number of flood events. When we look at these spatial connections, this is the spatial pattern we get. And when you look at this map, you see these 671 catchments in gray, and you see these black lines which connect pairs of catchments that have in the past co-experienced flood events. And I'm going to furthermore refer to these spatial connections as spatial flood dependencies. As you can see, these spatial flood dependencies, they're stronger in certain regions and weaker in others. And we have the Pacific Northwest and the West Coast sticking out as a region with important spatial flood connections, the Rocky Mountains as an important region where floods are spatially connected, and the Appalachian Mountains where spatial flood connectedness seems to be pretty high as well. Now, these flood events, they don't all happen in the same season, and we have distinct flood seasonalities across the United States. I've here mapped the mean date of flood occurrence for each of the catchments using different colors. where green colors and blue colors indicate mean flood occurrence in winter and spring, and pinkish or purple colors indicate mean flood occurrence in spring and summer. Floods occur mostly in winter along the west and east coast, and in summer in the Rocky Mountains, and there are some regions in the south with flood occurrence in fall. As these floods, they happen in different seasons, we would also expect that these spatial flood connectedness patterns may vary by season. We're here looking at the same picture, but just for the winter season, and we see that the pattern has changed. We see that the most important region in terms of flood dependencies in winter is the west coast, with some connections reaching inward, and these are caused by inland penetrating atmospheric rivers. And then we have some strong spatial connections in the Appalachian Mountains because of high soil moisture availability and the direct translation of precipitation into runoff. As we move into spring, we lose the spatial connectedness along the west coast, but we gain a lot of connectedness in the Rocky Mountains, where snow melt and snow accumulation processes are at play. And then we also still have high spatial connectedness in the east because of high soil moisture availability and some storm events. In summer, we lose most of the connectedness, but we retain some connectedness in the Rocky Mountains because snowmelt synchronizes event occurrence across catchments. And then in fall, finally, we've lost most of the connectedness, but we're gaining some connectedness again in the Pacific Northwest because of atmospheric rivers that start to kick in again. Some connectedness in the east because of frontal storms, and then interestingly, we even see the cyclonic activities in the south, which also seem to connect event occurrence across locations. Now, we were wondering whether these connections, they're solely a result of meteorological or precipitation processes, or we need soil moisture and snowmelt as land surface processes in order to explain these spatial patterns. In order to answer this question, we determined spatial connectedness not just for flood events, but instead we also looked at spatial connectedness in extreme precipitation events associated with flood events. We're here looking at a summary of the figures we've seen before for winter and summer, just that this time we're indicating connectedness not as lines, but we're actually counting the number of lines going out of a point, and the size of the dot indicates how many sites a specific catchment shows connections with. So again, high connectivity in the west and the east in winter, and high connectedness in the Rocky Mountains in summer. Now, do we see these same patterns in precipitation? Some of them, yes, some not. You can already see that these two maps, they look a bit different. And in order to have a closer look at these differences, we computed a difference map between the two, where we subtracted the blue map from the brown map. And in the difference map, you now see green catchments where spatial connectedness in discharge is higher than spatial connectedness in precipitation, and purple dots for catchments where precipitation connectedness is stronger than flood connectedness. We see that there's, again, distinct regions that pop out. In the west, spatial flood connectedness is higher than spatial precipitation connectedness. And this is because there's apparently something that enhances connectedness, and this can be because of high soil moisture availability in winter. In the Rocky Mountains, we have snow accumulation processes which prevent the direct translation of extreme precipitation events to streamflow events, and therefore we have a weaker spatial flood connectedness than extreme precipitation connectedness. The opposite is the case if we look at the summer picture, where now the Rocky Mountains have stronger streamflow connectedness than precipitation connectedness, because the snow that was accumulated in winter is now melting and it's synchronizing event occurrence across catchments. So in order to explain these flood dependencies, we cannot just rely on dependencies in precipitation, but instead we also need these important land surface processes such as snowmelt or soil moisture to explain the spatial patterns in flood connectedness. Now let's talk about spatial connectedness in terms of drought. So we're moving from high flows to low flows. And here we have a slightly different question. We're no longer looking at these spatial connections, but instead we're interested in drought extent, so how big a drought event is in space. And this is, as initially discussed, important because drought management gets much more challenging if several locations are affected at once. I'm here asking how the spatial drought extent in the United States has changed over time, over the period 1980 to 2018. I'm also asking which hydrometrological drivers govern these spatial drought extents. And we want to look at how the importance of these hydrometrological drivers has potentially changed over time. And as before, we're going to use the same data sets, which consists of nearly natural stream flow gauges in the United States. For this analysis, we're again for each of the catchments extracting drought events, and we're applying a similar procedure to the peak over threshold approach. That just this time we're interested in threshold, below threshold events, and we're, in order to identify these events, first smoothing the time series. This is typically done in drought analysis to avoid the extraction of dependent events. We're then computing a variable threshold that varies with season in order to focus on anomalies rather than absolute low flow events. We're then defining everything below this variable threshold as a drought event. These are stream flow drought events, so we're interested in hydrological drought. Once we've extracted these drought events for each of the catchments, we want to do the spatial analysis, and we determine a monthly extent time series, which tells us for each month which fraction of the catchments in the United States has jointly been affected by the drought event. So the larger the number, the higher the spatial coverage of the event we've been observing. And then we're also interested in knowing a bit more about the really large events, and we here define large spatial events as those events that affected at least or more than 20% of the catchments in our data set. Third, for this analysis of the hydrometrological drivers, we're looking at anomalies of different types of hydrometrological drivers. We're determining precipitation droughts, similar to how we determined stream flow droughts. We're for each catchment determining high temperature anomalies. We're for each catchment also determining snow water equivalent deficits and soil moisture deficits. And then for each of these drivers, we're looking at the overlap or the spatial overlap of stream flow drought occurrence with any of these anomaly types. And we're computing an overlap time series that determines for each variable the spatial overlap of the deficiency in that variable with the location of stream flow drought. So if we have an overlap of 100%, that means that all the catchments that experienced stream flow drought events, they also experienced, for example, precipitation drought. And that would be an overlap of 100%. If 50% of the catchments that experience stream flow drought experience a precipitation drought, that would be an overlap of 0.5 or 50%. And we do this overlap analysis for each of the anomalies separately. Now, let's first look at how spatial extents have changed over time. If we look at the period 1980 to 2018, you see here in brown the extent time series, and indicated with the dashed line a trend line, which already indicates that there's some increasing trend in these spatial drought extents. In gray, we've indicated some large events that affected at least 20% of the catchments in the data set. If we have a closer look at these large spatial events, we see that the spatial events, they clustered in time. There's an event cluster around the 1990s, another one in the early 2000s, and one that still seems to be ongoing. Now, if we look at where these trends come from, we can subdivide our data set into very large spatial events that affected more than 20% of the area, medium-sized spatial events between 10 and 20%, and rather small events or smaller than 10% of the area. And we can then compare the extents for an early period, 1981 to 1999, to a period 2000 to 2018. And we see that when we look at the big events and the moderate events, there's no real difference between the two distributions, while there's an increase in these smaller events that have increased in size. So these trends, these positive trends, the increase in spatial drought extents comes from increases in rather small events. Now let's turn to the hydrometrological drivers that cause these large spatially extensive drought events. We here have a picture of the January 1981 drought event, and indicated in orange again the streamflow drought events, with overlapped with the different hydrometrological driver deficiencies, in blue precipitation, in yellow temperature anomalies, in gray SWE deficits, and in green soil moisture deficits. For this particular event, we see a strong overlap of orange points with blue and soil moisture droughts, which means that there's a pretty high overlap of soil moisture and precipitation deficiencies with these stream flow droughts. We can repeat this analysis for other large-scale events and see that depending on the event, different types of drivers are more important. We have a mix of drivers in July 1988, mix or a more soil moisture and precipitation dominated event in the west, and the temperature in the east, and the temperature driven event in the west, and then an important event in terms of temperature anomalies in September 2002 and also in September 2007. We now want to summarize the importance of these different drivers over time, and I've here sorted the largest spatial events from January to summer and to winter again. For each event, we've plotted the overlap of specific anomalies with stream flow droughts. We see that overall soil moisture droughts show the highest overlap with stream flow droughts, and that precipitation is variably important depending on the event. We also see that temperature seems to be an important driver in the summer months, where temperature can be almost as important as soil moisture. Now we want to look at how the importance of these different hydrometrological drivers has changed over time. To do that, we're looking at the overlap time series of the different hydrometrological drivers with streamflow drought. So basically the higher the overlap, the more important is the driver for drought development. And we see that while there is hardly any trends for precipitation, SWE, and soil moisture overlap, there's an increasing trend in the importance of temperature as a driver of large streamflow droughts. And this is also seen if we just look at the large spatial events where temperature also becomes more important as driver, but at the same time, we also see a decreasing importance in precipitation and soil moisture as drivers of these large spatial events. Now, the importance of these hydrometrological drivers might change in space if we're located in different regions, and in order to assess the regional variation in driver importance, we're looking at these 9 different hydroclimatic regions, which are called the Bukowski regions, and each of these regions is pretty homogeneous in terms of their hydroclimate. For each of these regions, we're now going to look at trends in overlap, and we're going to map negative trends in brown and positive trends in green. And we're also going to distinguish between significant trends in solid colors and non-significant trends in transparent colors. We're looking at these trends for each individual hydrometeorological variable. We see a decrease in importance in precipitation for almost all the regions except for the Great Plains. We see an increase in importance for temperature in almost all of the regions. We see an increase in the importance of SWE deficits as a driver of streamflow drought in the Pacific Northwest. And we see a decrease in most regions in the role of soil moisture as a driver of streamflow drought. If we look at the ratio between precipitation and temperature anomaly overlap, this important role of temperature becomes even more apparent because temperature compared to precipitation has increased in most of the region. Now, the important role of temperature as a driver of spatial streamflow drought extents makes us think about future changes in these extents as we start to wonder how further increases in temperature might further change streamflow drought as spatial extents. And because temperature is increasing and it's importantly an important driver of streamflow drought extents, we might hypothesize that eventually streamflow drought spatial extents may also increase as we move into the future. However, this needs to be assessed using some sort of climate model output, and I guess that's the topic this group might be interested in. What do we learn from this first part of my talk? We've seen that spatial flood dependencies vary in time and space, and these spatial dependencies are importantly shaped by meteorological but also land surface processes. We've seen that spatial drought extents in the United States have increased over time, mainly because of increases in smaller droughts, and that different types of hydrometeorological variables are important drivers for individual drought extents or drought events. Now I want to turn to the modeling challenge. And modeling spatial extremes, statistically, it's particularly challenging because we have to not just model distributions locally, and we also not just have to model temporal dependencies. In addition, we also have to represent these spatial connections, which we have found to be important. I'm here going to introduce a stochastic model I've developed while at NCAR and at my previous position at WSL in Switzerland. And this stochastic model is able to simulate a large ensemble of flood events that are consistent in space. The stochastic model I'm going to talk about is called PRSIM wave, and it relies on the wavelet transform. And the goal of stochastic modeling is really to generate a large number of potential realizations of our phenomena. And here we want to try to simulate spatially consistent streamflow time series at multiple locations. So we want to generate a large number of streamflow time series that are not just realistic at one location, but are actually consistent with the series simulated for neighboring locations. The stochastic model as an input takes observed streamflow time series, and we're again going to fit the model to the 671 catchments in the United States, which we've initially been using. As an input, we take daily continuous flow, and to each of these series, we're going to fit a flexible 4-parameter kappa distribution, which is later on going to be used to simulate not just extremes we have observed, but it allows us to extrapolate to yet unobserved values. In a second step, we want to model the temporal dependence in our data, so the autocorrelation in our data. And in order to do this, we're transforming our time domain signal, so our input, to the frequency domain, where our signal is now represented by an amplitude signal and a phase signal, which tell us something about the intensity and the temporal shift of our data. This transformation is done by using the wavelet transform. Third, we want to also model the spatial dependencies in our data, and we're doing this by simulating one single white noise time series, which we're also transforming to the frequency domain using the wavelet transform. And here we're just interested in these random phases. We're using this one set of random phases to retain the spatial dependence in our data and at the same time to introduce stochasticity. How we're doing this is we're keeping our observed amplitudes and we're combining these observed amplitudes with the random stochastic phases. We're putting them together, applying the inverse wavelet transform, and we again go back from the frequency domain to the time domain. In this time domain, we now have generated a stochastic continuous stream flow time series, which is slightly different from what we had observed, but has the same distributional characteristics and similar autocorrelation characteristics. Now, the only thing this transformed signal doesn't have yet, it's not yet producing any unobserved magnitudes. And this can be achieved in step 5, where we use our flexible extreme value distribution to transform our signal from this original distribution to the kappa distribution. And this has the advantage that we can now simulate yet unobserved values. We can apply this model several times to generate a large ensemble or a large set of stochastic stream flow time series for different locations in our data set. We can now use these simulations to do different things. I've in the past used it to look at rare multi-year droughts, and I've also used it to study spatial flood events. Before we're now going to use the model, I just want to show you some model evaluation results, just that you believe me that this model is actually doing something valuable. And to show you this, I'm here showing you 3 years of observed stream flow in the upper panel for 4 stations in the data set, and 3 years of stochastically simulated data in the lower panel for the same 4 stations. And we see that the simulated signals are different from the observations, but they're also similar in the sense that they show similar autocorrelation, they show similar event occurrences, and they also show a similar distributions. Now we are using these simulations to extract the large ensemble of spatially consistent flood event sets, and these are the black events you see popping up here. And we now want to use these stochastically simulated spatial flood event sets as an input to a hazard assessment, where we're asking questions about very rare events which aren't part of our observed or usually short observed time series. So the advantage here is really that we can increase the sample size to study the frequency and magnitude of rare spatial events. If this presentation made you curious and you want to simulate some stochastic events yourself, I would like to invite you to download the R package PRSim, which will allow you to simulate events for a set of locations of your own interest. Now we're using these model outputs, these spatially consistent flood events, this large ensemble, to look at the probability of widespread flooding. And we need these simulations to answer such a question because we just don't have enough observations in our data set to look at such very rare events. So what we want to do here is answer the question of how susceptible large river basins in the United States are to widespread flooding. In order to answer this question, we take the stochastic streamflow simulations, which we've generated with PRSim, the stochastic model I just introduced. And we're again applying a peak over threshold extraction to extract for each of the basin's individual flood events, which we're again compiling in a binary occurrence matrix, similar to the analysis we'd done in the initial study I presented, where we looked at the spatial connections. And we're then doing a regional hazard assessment where we ask what is the probability that 70% of the catchments within one of these river basins is jointly flooded. For this assessment, we want to take two different perspectives. We first want to look at these 18 large river basins, which are meaningful in terms of water management. And then we're also taking a local perspective where for each catchment we define its own region as the radius for all the catchments in a radius around that station. And we want to ask the same question of how probable it is that 70% of the catchments within this radius are jointly flooded. Let's first take this river basin perspective where we're looking at the 18 river basins. What you see here is the probability that 70% of the catchments within one of these river basins are jointly flooded. The darker the color, the higher is the probability of regional flood occurrence. We see that regional floods might occur along the West Coast and in the East, and a little less frequently in the Ohio River Basin or the Columbia River Basin. And if you remember, these spatial flood connectedness plots I've earlier talked about, you might recall that we've seen high spatial connectedness along the West Coast and in the East. And this is partly reflected in these higher probabilities for regional flooding. We'd also initially seen that spatial flood dependencies vary by season, and this makes us think that probably also this hazard map might change if we look at different seasons, and this is indeed the case. We see the highest probabilities for regional flooding in spring, and that's a season where these spatial flood connections were strongest. We see pretty weak or low probabilities for regional flooding in fall. That's the season when we didn't see high spatial connectedness, and we see some probability of regional flooding in the East and the West Coast in winter. Now, these regions, they're relevant in terms of management, but they're also pretty inflexible. So we wanted to take a flexible perspective where for each catchment we defined its own region as the region within a certain radius around that catchment, as illustrated here by the red dot is the catchment of interest, and the black dots are all the catchments in the region belonging to that catchment. We again compute the probability of regional flooding and indicate probabilities by red colors, where again darker colors indicate higher probabilities for regional flooding. You see similar pictures as before, but this time the pictures are smoother because we don't apply these strict boundaries. We see again higher probabilities of regional flooding in winter along the West Coast in the East. These are the regions where spatial flood dependencies were also high. We see the Rocky Mountains stick out in spring and summer as regions where regional flooding might be possible, and in fall in the Pacific Northwest, and we even see Florida pop out. Now we wondered a bit whether we can better understand in which hydroclimatic regions there's a higher probability of regional flooding than in other regions. And we, in order to do that, grouped these catchments into different regions with a different stream flow behavior, and then looked at whether certain of these hydrological regimes show stronger probabilities of regional flooding than others. The subdivision we use is based on stream flow regime classes, so the mean seasonal regime of these catchments, and we've grouped the catchments into 5 different stream flow regimes, which you see depicted here. We have the green cluster that comprises catchments with a pretty intermittent stream flow regime with on and off stream flow phases. We have the weak winter regime in yellow, which is characterized by slightly higher flows in winter than in summer. We have the blue regime type with clearly higher flows in winter than in summer. The pink regime, which is a very expressed seasonal regime with high flows around Christmas and New Year's and pretty low flows in summer. And then we have the purple, the melt regime, with high flows in spring and summer and low flows in winter. For each of these regime types, we now summarized the probabilities of regional flooding for all of the catchments within one of these regions. And we here in these plots see the probabilities for the different seasons and the different regime clusters. Overall seasons, the New Year's regime, the regime with the strong seasonality, pops out as a region where we see high risk of regional flooding, and this is because in these regions all the flood events happen in that one season, and it's very likely that they happen at the same time and build a spatial flood event. Similarly, for the melt regime catchments, these are the catchments that flood synchronously because of snowmelt contributions that all happen around the same time. In winter, we see these pink clusters stick out again because of joint occurrence of flooding at around the same time. In summer, it's these melt regime clusters because of the joint occurrence of snowmelt. And in fall, it's again the pink cluster with some joint flood occurrences in the late fall month. So in order to have these higher probabilities of regional flooding, we don't just need flood occurrence anywhere in the region, but we instead need a homogeneity in the flood generation processes across that region, such that we will actually observe spatially large flood events, which then lead to a high probability of regional flooding. I'd like to come to an end by again summarizing the most important points of my talk. We've, in the part understanding, seen that spatial dependencies vary in time and in space because of different influences through meteorology and land surface processes. We've seen that spatial drought extents in the United States have increased over time, mainly because of increases in small streamflow drought extents. And we've also seen that the importance of temperature as a driver of streamflow drought extent has increased over time. I've introduced a stochastic model called PRSim, which you can download as an R package, and it's able to stochastically simulate large ensembles of spatially consistent streamflow time series, which you can use to study spatial extremes such as floods, but you could also look at spatial droughts or other types of phenomena. In the prediction part, finally, we've looked at how likely it is that a certain percentage of catchments within a river basin is jointly flooded. And we've learned that there's high variability or spatial variability in the probability of regional flooding. And we've also learned that we need homogeneity in flood generation processes within a region in order to achieve higher probability of regional flooding. I hope that in this talk I was able to show you that it's important to not just consider flood and droughts as local phenomena, but instead to study them in a spatial context where we consider the spatial dependencies between events, particularly if we want to do risk assessments. These spatial dependencies should be considered, otherwise you might either under or estimate the risk of regional flooding or also the risk of regional drought events. With this, I would like to end my talk, and I'm happy to answer any questions you may have now or later. If you want to reach out through email or Twitter, I'm also happy to have bilateral discussions about spatial extremes, about droughts or flood events. Thank you very much for your attention.
Thank you, Manuela. That was a fantastic talk. We'll be moving towards question and answer session now. There's a first question from Ala, and he says, you have considered different drought drivers. What about the groundwater impact, which is an influential compartment of terrestrial water storage changes in the US?
Thank you very much for this good question. I have to admit that in this work, we've totally ignored the subsurface. So we didn't look at groundwater, which is obviously an important part of hydrological drought too. We focus on the subsurface or on the surface system, just on stream flow droughts. But I agree, it would be super cool to look at spatial connections in groundwater drought. I would assume that these spatial connections in groundwater might be even stronger than the ones in stream flow, as is a more slowly reacting system than the surface system. I think in order to do that, we would just need to collect a good spatial database of groundwater. I'm not sure whether that exists for the US. In Europe, there's currently an initiative where different countries are working together to collect a spatial database of groundwater time series across different countries. And I think once this becomes available, there will be a great data set to look at these questions that help us to understand how groundwater droughts are spatially connected and how these connections in groundwater drought may differ from the connections we see in the surface system.
Thanks. So there was one slide where you were showing that the small events was increasing in 2020, 2000 to 2018 period compared to large and medium events. I think I missed the explanation. So could you explain like why the small events were increasing more, but not the large and medium drought events?
Yeah, it might have to do with the fact that we haven't observed too many very big events, and the sample is just smaller. But I just think that it has to do with the fact that these temperature driven events, they are becoming more frequent, and they're sometimes happening at smaller spatial scales because the events may be shorter, and the very extensive events, spatially extensive events, are usually also the longer events, and they may not solely be driven by temperature, but by different types of processes that in the past haven't been changing as strongly as the temperature as a driver.
Thanks. We have a next question from John. John says, thank you for this fascinating seminar. In subhumid and dry regions, there can be a contributing area for stream flow that is much smaller than the river basin area and is variable. It is especially problematic for large river basins in the Great Plains and similar. Did you or could you take this into consideration when addressing the linkages between meteorological soil moisture sweet drought to stream flow drought or conversely flooding?
I think I didn't fully grasp the question. I'm sorry. Could you, or is it in the Q&A box? Then I can maybe.
Yeah, I can repeat it again. In subhumid. Would you like me to repeat it again?
You mean when the.
So in subhumid and drier regions, there can be a contributing area for stream flow that is much smaller than the river basin area and is variable. It is especially problematic for large river basins in the Great Plains and similar regions. Did you or could you take this into consideration when addressing the linkages between the meteorological soil moisture, drought to stream flow drought, or conversely flooding? Or if you stop sharing screen, you can also see the Q&A box.
Yeah, I'm there now. I think I still don't fully get the point, but yeah, the problem is a bit we're here looking at catch. Oh, John is actually there. Maybe yeah, John, you can clarify your question for me.
No, hi. How are you doing?
I'm good. How are you?
Good. It's the issue is in river basins like the Missouri, and also when you get into the desert Southwest, you have areas where a lot of stream flows contributed, say in the mountains, and you have more or less exotic rivers traveling through the plains of the desert regions where they pick up very little runoff. We have this in Western Canada too. So anyway, I was wondering how can you address that when you're looking at these spatial statistics, and particularly between things like soil moisture, precip, SWE, and you know, it's really different when you go to the Appalachians where things are, say, very well connected, and runoff can occur quite readily through most parts of the river basin.
Yeah, thank you for the clarification. I think I understood the question now. Yeah, that's great. We mostly focus on headwater basins, so we're not really considering travel times or, you know, drivers that can influence stream flow in a very upper part of the catchments versus the downstream part. We're kind of avoiding this problem by just looking at headwater catchments. I think if you wanted to look at spatial connections in large river basins where the flow might have been traveling through the basin for a while, you certainly have to consider longer travel times than we did. And then you would have to also consider, if you wanted to look at the drivers, you would have to look at the drivers not just in the downstream part of the basin, but you would have to look at the drivers of stream flow drought in the headwater basins, and potentially, I guess, also at the role of water management that is happening along the stream, which might become increasingly important as you move through the basin. So the bigger the basin, the bigger probably the influence of regulation on the spatial connections, and the smaller the influence of the process, the hydrometrological processes that are happening in the upstream part of the basin.
Okay, great. So you stayed with headwater catchments. What would be a typical or average catchment size then that you looked at?
Yeah, it's anything between 500 square kilometers and I think roughly 2,000 square kilometers.
Okay, okay. Yeah, so some still getting pretty big, but you probably have mostly avoided the problem, I think.
Mm-hmm. But a very good point if we want to change scale.
Yes, well, it's a water management interest, right? Because if your river is coming from an area that's not experiencing drought through an area that has drought, then of course the water use is wildly different, and the impact is very different.
Mm-hmm. Yeah, I agree. And this is again, you know, how we use the water is again going to impact the spatial connections in drought occurrence. So I think the human impact can actually either aggravate or alleviate the spatial connectedness of droughts or flood events.
Yeah. Thank you.
The next question is from Martin. So Martin says, a very interesting analysis. Thanks. To what extent is your research useful to help understand the spatial variability of floods and droughts outside the US? How will you build on this research now that you are in Europe?
Hi, Martin. Thank you for your question. I think that's a very interesting question. I think in Europe, probably things are looking to some degree similar. I mean, we have mountainous regions which are probably behaving similarly to the Rocky Mountains, and where we expect high spatial connectedness in flooding in the spring and summer months. We have regions with a temperate, humid climate, which are precipitation driven. I think there we could probably learn something from the Appalachian Mountains and possibly from the West Coast. I think we need to take into account that maybe the climate can be a bit more continental in some places. And if we wanted to transfer this further to even more different regions, such as tropical climates or Arctic climates, I think we would have to look into other types of processes that might drive these spatial connections. I guess the snow processes will become more important, than maybe also ice processes and things like these, which we haven't been considering here as drivers or as potential drivers of flood connections.
The next is from Yusuf. It's not a question, it's information. So Yusuf says, I bring to your attention Dr. Saji Cohen from the University of Alabama, who runs a floodwater depth database in the USA. So maybe he wants to say that that database could be related for this kind of analysis. And
floodwater depth database, yeah. I think that's a very, very good comment. I'm going to write that down and eventually look at it. We're actually at the moment looking into some water depth data over the United States, but in a slightly different context than the spatial one.
Thanks. I don't see any more questions, so I'll just give a few seconds if anybody has any last question that they want to ask before we formally close this webinar. Just waiting for that. I just want to quickly ask, like, because you also mentioned about the ice, and when you were doing this kind of analysis in the US, I was looking at the ice and flood database of the US Army Corps of Engineers, and then they have almost like more than 2,200 ICM related flood events. So did you have any chance to look at those regimes or anything like that?
No, not at all. Honestly, this is kind of a type of flood event that I'm not super familiar with. I mean, I know that in the past there's also been quite a few of these events in Europe, but they're so rare these days that I've never probably paid enough attention to them, and neither did I probably pay enough attention while I was in the US. But I totally see that, from a Canadian perspective, this is a very important process to look at. But I also have the feeling that these types of flood events, they're often missing in these flood classification schemes. I think I haven't come across a flood classification scheme that includes these ice jam floods. It seems to be a geographically very, maybe not necessarily a small area, but an area where maybe not too many people live, and therefore maybe it's not getting too much attention as a plot generation process.
Thanks. I don't see any more questions, so we'll be moving towards the conclusion of the seminar. I want to thank you again, Manuela, and I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. Just a note that next week, Dr. Gerard Bells from Quasi will be providing a webinar on collaborative and reproducible modeling. So please stay tuned. That will be all for today. Thank you again, and please stay safe. Wish you a good day. Manuela, do you want to say any last comment?
Yeah, thank you for joining. It was a great evening, and I mean, for me, it was an evening. And I hope to see as many of you as I can sometime in person at maybe a conference.
Bye, everyone.
Bye.